Welcome to the lecture on comparing classifiers. Part of the material presented in this lecture is taken from the following book, while transcription and interpretation errors are responsibility of the lecturer. This lecture introduces the following concepts: confidence interval, empirical accuracy, and hypothesis testing, with specific reference to different test sets and the same test set. You find yourself in the following situation. You want to use the customer calls database provided by the CEO of the telecom company to develop different classification techniques to find which is the best classification model for solving the churn problem. However, the concept of best classification model is extremely difficult to define, and you know that what is needed to start is to compare the accuracy achieved by different classification models from different classification techniques. Indeed, you know that it is often useful to compare the performance of different classification models to determine which one works better on a given dataset. However, you know that depending on the size of the data, the observed difference in accuracy between two classification models may not be statistically significant. In particular, you take into account the following situation. You have an inducer A which achieves an accuracy equal to 0.85 when tested on a test dataset consisting of 30 records, and you also have another inducer B, which achieves an accuracy value equal to 0.75 when tested on a test dataset consisting of 5,000 records. Then you are left with this question. Is inducer A better than inducer B because it achieved a greater accuracy value? In such a setting, two key questions regarding the statistical significance of the performance metrics are raised. The first one concerns the fact that although inducer A achieved a higher accuracy value than inducer B, it was tested on a smaller test set. Therefore, the question to be answered in this situation is the following. How much confidence can we place on the accuracy for inducer A? The second question to be answered is the following. Is it possible to explain the difference in accuracy as a result of variation in the composition of the two test datasets? The first question is concerned with the issue of estimating the confidence interval of the accuracy for the two inducer A and inducer B, while the second question is related to the issue of testing the statistical significance of the observed deviation, so the difference in accuracy between inducer A and inducer B. To provide a formal treatment of the situation, we consider the task of predicting the value of the class attribute for a test record as a binomial experiment. In such a setting, then, we consider a test set D capital N containing N records, and we let X be the number of records correctly predicted by a given inducer, and we let P to be the true but unknown accuracy of the inducer. In such a situation, we can model the prediction task as a binomial experiment as already mentioned, and thus X is a random variable which has a binomial distribution with mean equal to capital N times P and variance equal to capital N times P times 1 minus P. Furthermore, the empirical accuracy, which is defined as follows: X equal to the ratio of X to N, so is the ratio of the number of records correctly predicted by the inducer divided by the total number of records to be predicted, will be a random variable having a binomial distribution with mean equal to p and with variance equal to p times 1 minus p divided by capital N. Although the binomial distribution can be used to estimate the confidence interval for the empirical accuracy, it is often the case that we prefer to approximate the binomial distribution by a normal distribution, and this can be efficiently done when the number of records of the test dataset is sufficiently large. This approximation is usually due to a matter of simplicity. Then, in this situation, and based on the normal distribution, the following confidence interval for the empirical accuracy is obtained. This formula simply states that this amount, this quantity, substantially this difference, which is the difference between the estimated accuracy and the true but unknown accuracy, divided by the ratio of p times 1 minus p divided by n, which is the standard deviation of the random variable, lay in this interval where the extremes are these that I am evidencing now, and this happens with probability 1 minus alpha. However, we have to clarify what z of 1 minus alpha divided by 2 is. This is simply the quantile of the normal distribution, and it is that value such that the area, the blue area that is evidenced in the picture, is equal to 1 minus alpha, where alpha is typically called the significance of the confidence interval, while 1 minus alpha is called the confidence of the confidence interval. However, we wonder what we can do, how we can exploit this formula for our goal to compute the confidence interval of the accuracy of a classifier. The answer to the previous question is as follows. Rearranging the above inequality leads to the following confidence interval with significance alpha and confidence equal to 1 minus alpha for the true but unknown classification model accuracy. The confidence interval is then the following. This is the lower limit of the confidence interval. This is the upper limit of the confidence interval. And by definition, the true but unknown accuracy of the classification model will be contained in this confidence interval with probability equal to 1 minus alpha. Let us now show how to exploit what we have derived concerning the confidence interval for the true but unknown value of the accuracy of a classifier. Given a classification model achieving an empirical accuracy equal to 0.8 on a test dataset consisting of 100 records, so in this case capital N is equal to 100, we want to know the confidence interval for its true accuracy with a confidence level equal to 95%. In this case, then, according to what we have shown and derived before, the 95 confidence interval level corresponds to a value of the quantile z of 0.975, which is equal to 1.96. This value can be obtained from the tables of the normal distribution. This brings to the following confidence intervals for the true but unknown accuracy value of the considered classification model: 0.711, 0.8767. So we can state that the true but unknown value of the accuracy of the classification model achieving an empirical accuracy equal to 0.8 on a test dataset consisting of 100 records is contained in this interval 0.711 0.867 with probability equal to 0.95. In such a situation, however, we can ask ourselves what happens when the number of records capital N increases. So what's happened to the confidence interval about the true but unknown value of the accuracy of the considered classifier? To clarify what's happened, we use this graphical representation, which shows us how the amplitude of the 95 confidence interval for the true but unknown accuracy changes depending on the dimensions of the test set, which is represented by capital N. In particular, the blue dashed line represents the lower limit of the confidence interval, while the gray dashed line represents the upper limit of the confidence interval. It is clear from this graphical representation that increasing the dimension of the test dataset shrinks the amplitude of the confidence interval, which theoretically should shrink towards the true value of the accuracy of the considered classification model. However, it can be seen from this picture that while the amplitude of the confidence interval dramatically reduced or rapidly reduced when we increase from 100 to 300 to 500 to 700 and to 900 the dimension of the test dataset, the amplitude will shrink always less when we increase further the dimension of the test dataset. This is due to the fact that the amplitude of the confidence interval is proportional to the square of the cardinality of the test dataset. Let us now focus our attention to the issue of comparing different classifiers, and in particular we start by focusing our attention to the case of different test sets, so in the case where two classifiers must be compared but two different test sets are used for their comparison. In such a situation, consider two classification models, M1 and M2. While M1 is evaluated on a test set D1 containing N1 records and achieves an error rate equal to E1, the model M2 is evaluated on a test dataset D2 containing N2 records and it achieves an error rate equal to E2. So in such a situation, we have that the two test sets D1 and D2 are assumed to be independent. Our goal is then to test whether the observed difference between the error rate of the first classification model and the error rate of the second classification model is statistically significant or not. To formally address the problem of comparing two classifiers in terms of their errors in the case where different test sets have to be used, we assume that N1 and N2 are sufficiently large and such that the error rates E1 and E2 associated with the classification model M1 and M2 can be well approximated using two normal distributions. Furthermore, if the observed difference in the error rate is denoted as D, so if D is defined to be the difference between the error rate associated with model M1 and the error rate associated with model M2, then D is a random variable which is distributed according to a normal distribution with mean equal to dt and with variance equal to sigma d squared, which is not known. This variance, so the variance of D, can be estimated as follows. Sigma d squared is approximated by sigma d squared at, which is equal to E1 times 1 minus E1 divided by N1 plus E2 times 1 minus E2 divided by N2. Then the confidence intervals for the true difference dt between the error rates of the two classification model M1 and M2 is obtained to be the following, and this is the lower limit and this is the upper limit. In particular, sigma at d is the square root of sigma d squared hat as defined. Let us now show how the derived confidence interval has to be used to compare two classifiers in terms of the achieved error where different test sets have to be used. First of all, we have to say that three different cases are possible. In the first case, the following condition holds. 0 belongs to the confidence interval that we have computed. If the confidence interval spans the value 0, we conclude that the observed difference d between the error rates of the first and on the second classifier is not statistically significant at the alpha level or with confidence equal to 1 minus alpha. Therefore, in such a situation, we will conclude that classification models M1 and M2 are not significantly different in terms of achieved error at the alpha level of significance or with confidence equal to 1 minus alpha. In the second case, we have that the following inequality holds. Then, if the upper limit of the confidence interval, so if this upper limit is negative, then the classification model M1 is better than the classification model M2 at the alpha divided by 2 level, or with confidence equal to 1 minus alpha divided by 2. In the third and last case, we have that the following inequality holds. Then, if the lower limit of the confidence interval, so if this lower limit of the confidence interval is positive, then the classification model M2 is better than the classification model M1 at the alpha divided by 2 level, or with confidence equal to 1 minus alpha divided by 2. We now focus our attention to the case where two classifiers have to be compared, but in this case we can use the same test set. Consider two classification models, M1 and M2, to be compared using the k-folds cross-validation procedure. We let D be the dataset to be partitioned into capital K disjoint subsets, which we know are exhaustive, so they form a partition of the available dataset D, and with almost a constant number of records. We recall that we usually let D1, D2 up to D capital K to represent a partition of the available dataset. We then apply classification techniques to construct a classification model M1 and M2 from k-1 of the partitions and test them on the remaining partition. This step is repeated capital K times, and each time using a different partition as the test dataset. We furthermore let M1K be the inducer for model M1 obtained at the kth iteration, and M2K be the inducer for the model M2 obtained at the kth iteration. Then each pair of models M1K and M2K will be tested on the same partition K. In such a setting, we let E1K be the error rate associated with M1K and E2K be the error rate associated to M2K. The difference between their error rates, so the error rates m1k and m2k at the kth iteration. The kth fold of the k-folds cross-validation can then be written as follows. dk is equal to e1k minus e2k. So e1k is the error associated with model M1 at the kth iteration of the k-folds cross-validation. The same applied to e2k, which is the error achieved by the model M2 at the kth iteration of the k-folds cross-validation. If capital K is sufficiently large, then decay is normally distributed with mean equal to dtCV and with the standard deviation equal to sigma CV. Then the overall variance in the observed differences can be estimated using the following formula. Sigma dCV squared at is equal to the summation which ranges over all folders of dk minus the underscore square divided by capital K times k minus 1, where the overlined is equal to 1 divided capital K times the summation of the decay ranging across all folds of the k-folds cross-validation. Under this setting, we use the student t distribution to compute the confidence interval for the value of the true mean dtCV. In particular, the resulting confidence interval is the one that is evidenced here, where the only difference with respect to the confidence interval that we have presented before in the case of different test set is represented by the fact that here we use t of 1 minus alpha divided by 2 k minus 1. Where indeed this term is obtained from the probability table of the student t distribution with the confidence equal to 1 minus alpha or significance equal to alpha and with k minus 1 degrees of freedom. Concerning the use of the confidence interval to establish statistical significance, we have the same consideration that we have made before for the case of the comparison of classifiers in the case where different test sets are available. If the confidence interval spans the value 0, we can conclude that the observed difference is not statistically significant at the alpha level of significance or with confidence 1 minus alpha.